So let's start again with a coordinate system. And on this coordinate system, I'm going to put down a right angle. So we have our initial side and our terminal side. Now, a right angle, because it's so popular to have a 90-degree angle, that the right angle does get another special symbol here, this square. And a square specifically means that you're dealing with a 90-degree angle. Now, it's also important to start connecting degrees with radians. So 90 degrees is pi over 2 radians. And this is the right angle that we talked about in the last lecture. And also, don't forget about the square box here, does mean 90 degrees. But what we're going to do with the right angle is we're now just going to connect these lines to make this a right triangle. So a right triangle is any triangle that has an interior angle of 90 degrees. So any triangle, if there's an interior angle that's 90 degrees, then that's a right triangle. So this right triangle, we need to develop some type of procedure here to name things so that we have some common understanding of what we're talking about on the right triangle. And so first is to label some sides. Now there's no particular way of labeling sides, but it is pretty common to label things in a counterclockwise rotation because that's a rotation math considers positive. So notice that my labeling of A, B, and C is in a counterclockwise rotation. Now again, this isn't rigid, this type of thing, but it's pretty common to label things like this. But there are some things that are rigid, and that has to do with where we choose an angle. So we know this is the right angle, that's 90 degrees. These two angles here, though, are not 90 degrees. We don't know what they are. So imagine down here, this angle is actually an eyeball. Now, each of these legs has a name. The only name that stays consistent is hypotenuse. The hypotenuse is always the longest leg. The longest leg is always the hypotenuse. That never changes. What changes is what we call A and B. And what we call A and B depends on which angle you choose. So imagine this eyeball is our angle. And the eyeball always looks at what we call the opposite leg. And so if we choose this angle here where the eyeball is, then we would call A the opposite leg. And then we would call B the adjacent leg, because B is adjacent to the eyeball, and A is opposite the eyeball. Now, this same terminology is true if we move the eyeball to this other angle position. If we would look at this angle up here, now the eyeball is looking at side B. And in this scenario, we would then call side B the opposite leg, and we would call A the adjacent. So adjacent and opposite depend upon how you choose your angle. The angle always looks at the opposite leg. The only thing that remains consistent is the hypotenuse. The hypotenuse is always the longest leg. So let's just take a look at our right rectangle again. And we're going to put an angle here. And choosing this angle. So if I assign this my angle, that means the angle is looking, remember the angle always looks at the opposite leg. So then this is what we call opposite. And then we say this is adjacent to the angle. And we're going to take this right rectangle and compare it to other ones. Now, I have 3 right triangles here. And all of these right triangles have the same angle here. All these angles are the same. However, everything else is different. They all have a different hypotenuse. They all have different opposite legs. They all have different adjacent legs. Everything about these right triangles is seemingly different except for the angle. The angle looks to be the only thing that's the same here. And I could take these 3 right triangles and I can actually line them all up. So here are all 3 of those right triangles lined up, and you can see they all overlap each other because they all have the same angle. But what turns out to be true is there's more in common here than just the angle. And that's not at all obvious by just looking at this picture. Let's go back to our single right rectangle again to discover what it is these have in common. And what's in common are all the ratios we can form with these legs. So here is a ratio. Ratio means something divided by something. So the opposite divided by the hypotenuse. That's a ratio. Now, altogether, there are 6 ratios we can form here. We can do the opposite divided by hypotenuse. We can do adjacent divided by a hypotenuse. We can do opposite divided by adjacent. Hypotenuse divided by opposite. Hypotenuse divided by adjacent. And the last possibility is adjacent divided by hypotenuse. Adjacent divided by opposite. These are the 6 ratios we can form from these legs. Now, why would we do this? Well, it was discovered probably at least 2,000 years ago, that these ratios, all 6 of these ratios, are the same for all right rectangles if the angle is the same. So what do I mean by that? Let's go back to our picture of the 3 rectangles. Right triangles. So if we look at these right triangles, I'm labeling the opposite and hypotenuse on all of these right triangles. And this ratio, the opposite divided by the hypotenuse, this ratio is exactly the same for all 3 of these right rectangles. So let's say the opposite divided by hypotenuse, let's just say this equals a half. Oops, can't quite fit that on the screen. I'll do it over here. Let's just say this equals a half. That's true then for every right triangle. So not only do these have the angle in common, But they also have in common all 6 of these ratios. They're all the same for all right triangles that have the same interior angle here. So all 6 of these ratios are the same for all right triangles that have the same angle here. So there's more in common than just the angle. What's also in common with other right triangles is these ratios. And these ratios over the years have been given names. And let's go through them. Starting with this first one. This ratio is called the sine function, the cosine function, the tangent function. This is cosecant. This is secant. Secant. And this is cotangent. So all 6 of these ratios, because they've become so important over the years, they've gotten their own names. And these are the names of these ratios. And you are expected to memorize these. Now, there are a lot of relationships in trigonometry. And maybe somebody has them all memorized. I certainly don't. And I will be giving you pages. I will be giving you handouts through the semester of what these relationships are. And there are a lot. And so it's my position that you should memorize the ones that are most common. And then as we go forward in the semester, I will make you aware of other relationships, and I'll give you a handout of that. But the other relationships that aren't as common, I don't expect you to memorize. But the common ones, I do expect you to memorize. And I say that because if trigonometry is going to be in your future career, then there is no question that you will want this burned into your brain. There's no question about it. If trigonometry is in your future, you've got to have this in your brain. These are the basis, really, of trigonometry, these starting 6 functions. Now, there is kind of an acronym to help you memorize this stuff. And so to get to this acronym, I'm first going to shorten all of these expressions. So instead of opposite over hypotenuse, I'm just going to call this O divided by H. And you can see I did that for everything. I just shortened all the words to the first letter. And if you do that, we get this silly little saying here. That's pretty common. SOHCAHTOA. And this is meant to help you memorize what these 3 relations are right here. So SOH means sine divided by equals opposite divided by hypotenuse. The CAH means the cosine divided by equals adjacent divided by hypotenuse. And the TOA is tangent equals opposite divided by adjacent. So SOHCAHTOA is a way to help you to memorize these relationships here. And 100% you should memorize this. So SOHCAHTOA helps us memorize this. Well, how do we get these 3 over here then? Well, notice that sine is the ratio of opposite divided by hypotenuse, while cosecant is hypotenuse divided by opposite. In other words, these are the reciprocal of each other. And that's true for all of these. And because these are the reciprocal, means then we can just write that. So cosecant is 1 over sine. So once you know sine from SOHCAHTOA, then you can just do 1 over sine to get cosecant. And you can do the same for the rest. So once you know SOHCAHTOA, you can then do cotangent, because you will know then cotangent is 1 divided by tangent. So these are all things you absolutely 100% should burn into your brain. Everything right here. And there's actually one more thing I have to add to this. If you look at the tangent function, notice it's opposite over adjacent. Now, we can get opposite over adjacent by using sine and cosine. So if we do sine divided by cosine, we will get tangent. Because sine divided by cosine means these h's will divide each other out, and you're just left with opposite over adjacent, which is the tangent function. Now, the same is true for cotangent. Cotangent is cosine over sine. Because remember, these are all the reciprocal relationships. So this right here, all of this, you should burn into your brain. And 100%, if trigonometry is going to be in your future career, you will know this for the rest of your life if you have trig in your future career. Now, I want to focus on these two here for a moment, because there's something else that you're going to want to memorize here. And that is the common angles, I'll say. So there are some angles that give us nice exact answers. And these are very common angles to see. So common that it's expected that you memorize these. So for sine, these common angles, 0, 30, 45, 60, 90. And I also gave their radian equivalents, because these are all things you're supposed to be learning here. Not only are you learning degrees, but you should also be learning radians. And there is a pattern to the output. So if you notice over here in the output, everything is always divided by 2. And if you look at the numerator, it increases. It goes 0, 1, 2, 3, 4. And it's all under a square root. That's the pattern. Now, these do simplify. So square root of 0 divided by 2 is 0. So the actual numbers you want to memorize here are these. But I wanted to show you what the pattern is, because sometimes if you know what the pattern is, that also helps you memorize these numbers. And something else about the sine function is that notice as our input increases, so does the sine function. And here is a graph of the sine function from 0 to 90. And you can see the sine function is increasing. And these are all things to help you memorize these numbers. So sine of 60 is square root of 3 over 2. Sine of pi over 2 is 1. Now, all of these same numbers are also used in cosine. However, with cosine, as the inputs get larger, cosine actually gets smaller. And again, here's the cosine function. You can see the cosine function actually decreases. So if you look at cosine, it's the same inputs. And it's actually the same outputs. These are the same outputs. They've just been flipped. These outputs are increasing, but these outputs over here are decreasing. They're the same numbers, just in a different order. So notice cosine goes 4, 3, 2, 1, 0. It's decreasing. So again, you should burn this into your brain. These are very common angles, and it's good to know these answers. And what's going to happen in the future as we move forward in our class is we're going to learn how to get larger angles. Angles larger than 90 degrees. And getting these larger angles will entirely rely upon you knowing these. So we can figure out larger angles based upon these. We're not doing that now. We'll do it in the future. But I'm just trying to stress, don't blow this off. I know we're only in the second lecture, and there's already a lot to remember. But there's a lot of groundwork to lay here to start off trig. So, with that said, Pythagorean theorem. This is a pretty big deal. The Pythagorean theorem is incredibly useful. And it applies to right triangles. And so I have my standard convention here, ABC, written in a counterclockwise way. And the Pythagorean theorem is a squared plus b squared equals c squared. And what I want to do here is just show you quickly why this is true. So currently, as of today, there's at least over 300 proofs of the Pythagorean theorem. And I want to show you one that's more from the ancient times, because I think it's interesting how they thought about things. Because they thought about things really in terms of shapes 2,000-3,000 years ago. And so I'm going to take this right triangle, and I'm just copying it. I'm going to paste it over here. But instead of 1, I'm going to paste in 4. These are all the same. All I did is copy and paste. They're all the same. And what I'm going to do is I'm going to put these together in what is seemingly a strange way at first. And somebody figured this out at some point, not quite sure who gets credit for having figured this out. But all I'm doing is taking all these right triangles and putting them together in this kind of seemingly goofy way. And there we go. Now, inside here, you can see there's a square. And going back to what we're labeling these sides, you can see that these long legs are the hypotenuse. So all of these are the hypotenuse here. This is also C over here. And this is C. And this is C. And what that means then is that the area of this black rectangle then is C squared. So this black rectangle you're seeing has an area of C squared, because you can see it's a square with sides C. Now I'm going to put a box around this. And let me just color that really quickly. So there's the box. Now if I move this right triangle and just stick it right here, what is the area of this black region? Well, the area of this black region is still C squared. Just because I moved this doesn't mean the area of the black changes. It doesn't. Just because I move one of these doesn't change the area of this black region. It's still C squared. So what I'm going to do is I'm going to put these right rectangles together in a different way. And look at that. Now, if you look, this is side A. This part of the right triangle, we labeled as side A. Which means then the area of this black square must be A squared. Now, if we look at the other black rectangle, or actually squares, I should say, this is side B. So this right here is side B. Why did that not change to white there? And this is also side B of our right triangle. And since that's true, means this black square then must be B squared. And so what have we just proved? We just proved a squared plus b squared equals c squared. Now, there are over 300 proofs. Some more simpler than others, some more clever than others, but I liked this one and the way it uses shapes to prove this math formula. And that's why a squared plus b squared equals c squared, the Pythagorean theorem. And there's actually more things that are even more interesting about the Pythagorean theorem that maybe we can talk about sometime in the future, but I don't want to get overly complicated with this right off the bat. This is what you need to burn into your brain, the Pythagorean theorem. Now, the Pythagorean theorem can be used for many things, but for us, there's another thing that we're going to use with it. And to see that, we have to go back to our right triangle. And I'm just going to use the sine function here. Now, the sine function is opposite over hypotenuse. And if we look at what I have labeled here, you can see the opposite I'm calling A, and the hypotenuse I'm calling C. So I'm just going to change that down here. And so sine of theta here is A over C in terms of our right triangle. Now what I'm going to do with this is multiply both sides by C. So that'll cause these C's to cancel out. And what are we going to do with this? We're going to plug it in to the Pythagorean theorem. We're going to plug it in right for A. And that's what we get. Now I'm going to do the same thing, but with cosine. Now cosine is adjacent over hypotenuse, and I had to spell out adjacent here so you didn't get confused with this A and this A because they are not the same. Because you can see the adjacent leg is B. So the adjacent leg is B, and the hypotenuse is C. And again, I'm going to multiply both sides by C so that these C's cancel out. And we're going to take this and stick it into the Pythagorean theorem. And now something cool happens here. So using properties of exponents, we can take the 2 and pass it along to sine and pass it along to the C. So if you remember about properties of exponents, the exponent can pass along to each factor. And same with this one over here. And if we do that, we'll get this expression. Now, what's cool about this is if we divide everything by C squared, we get this hugely important relationship. I can't tell you how many times I've used this. It's very common. It's called a Pythagorean identity. Now, there's actually 3 Pythagorean identities altogether, and we'll talk about the other 2 more into the future. But this one is huge. This one is used so much that I'm just going to be silly about this and nonsensically draw all these arrows towards it. You should 100% burn this into your brain. An incredibly useful relationship. A Pythagorean identity. Sine squared. Now, usually, a lot of times the angle's kind of shortened. So a lot of times I say sine squared plus cosine squared equals 1. So I'm being a little lazy there and not saying the angle. A lot of times it's that way. Sine squared plus cosine squared equals 1. Hugely useful. So here we go. Looking at the lecture work, here is question 1. Given this right triangle and that our angle is up here, which of these letters represents the opposite leg? So the angle always looks at the opposite leg. And so the opposite leg is B. Here's question 2 then for the lecture work. Given this right triangle, and because you probably haven't memorized this stuff yet because you're just seeing it now, here's the sine function relationship. And I want you to find the value for A using the sine function. Now, no calculators needed here. In other words, I just want the expression. Don't give me the decimal number. I just want the expression. What is the value for A? So if we look here at sine theta, I apologize here. I can actually write halfway decent with my mouse if I go a little bit slower. So sine theta, looking at this here, it's opposite. It's opposite. The opposite leg here is A. And that's divided by the hypotenuse, which is 10. And we want to find the value for A. So all we're going to do is solve for A, which means we'll multiply both sides by 10. And now our angle, I put sine theta here. I'm giving you the angle, though. It's 30 degrees. Oops, I ran out of screen space there. And so that's A. 10 sine 30. Here's question 3. Same deal, no calculator needed. Using the cosine function, what is B? So we have cosine 30. And this equals the adjacent. The adjacent leg is B divided by the hypotenuse, which is 10. So to solve for B, we multiply both sides by 10. And that is the value for B. 10 cosine 30. So how about this then for question 4? Using the Pythagorean theorem, and again, no calculator needed, what is the value for A using the Pythagorean theorem? Well, the Pythagorean theorem says A squared plus B squared equals C squared. We don't know what A is, but we do know what B is. B is 7. And 7 squared is 49. We also know what C is. C is 10. 10 squared is 100. So A squared must be 51. And so A must be the square root of 51. And that's our answer. So in summary, and this will happen from time to time, but in summary, see the attachment. So I'm going to give you attachment if you didn't already notice in the modules of Canvas with this lecture video link. There's also a link there to an attachment I'm giving you that lists out everything you should memorize for this section. And I'll be doing that for some more lectures in the future where the summary is so large that I'm going to give you a handout for that. And that's our case today. The summary is see the attachment. And that's lecture 2.